we'll look now at the law of conservation of momentum. So you know it's important because it says it's a law. That's sort of how we rank things. Um, and to sort of get here, let's consider collisions and Newton's third law. So we've got two masses here. You can see from the looks of it, mass A is greater than mass B, although we don't know. Maybe it's styrofoam, the other one's lead. But let's just assume the actual masses don't matter, and they've both got their individual speeds or velocities, I guess technically. So during this collision, as we know from dynamics and Newton's third law, right, the force of A on B is equal to the force of B on A, even if it is the case that, let's say, mass B is just sitting there with V equals 0, right? And mass A comes along, and maybe mass A is much bigger or greater, and it hits mass B, and mass B goes flying off, right? We know that whatever the force on B is from A, that's also equal to the force on A, right? It just might not do as much, right? And that's a real key idea of Newton's third law, right? When you jump off your table, technically the force of the earth on you is the same as the force you have on the earth. It's just the earth is so massive it doesn't actually, it's not worth calculating the acceleration of the earth, but you could. So we can write it that way. I'm saying it this way. So this is the force of A on B, just to write it that way. And that would be equal to the force, the negative of the force of B on A, right? So it's going to be in the opposite direction, but equal in magnitude. We can take that equation, multiply both sides by delta T for the collision, and especially because the time of this collision will be the same for both of them, right? The time they're in contact, and whatever the force is at any point in time, right? Those two would be equal. Then we can look at the total momentum of the system, which is, in this case, we've got our entire system is mass A and mass B, right? So before the collision, the total momentum of the system is just whatever the momentum of mass A is plus whatever the momentum of mass B is, right? That's it. After the collision, though, because there is a collision, right, and we just saw how the change in momentum is the impulse, right? So if we just look at mass A, that's this part here, right? The momentum of mass A is whatever it was before the collision. That's the first part here, that was the momentum of mass A, plus the impulse it experiences, right? That is the force of B on A times whatever delta T is. And then we can have the same analysis for mass B. We can say the momentum of mass B after is whatever it was before, which we've just indicated as PB, plus the force of A on B times by delta T. Then we can take our handy dandy equation and we can say the force of B on A, right? Remember up here, we can take that and we can substitute that in down here and replace the force of A on B with the negative of the force of B on A times delta T, right? So we can just replace that. And then we can recognize that if we look at this equation for the total momentum of the system after, this and this cancel out, right? And so we're left with momentum of A plus momentum of B, which, remember, was the exact momentum of the system before the collision. And that leads us to this very, very important law, which is written out here in words, but if you just look at those two sides, you can equate them, right? But in words, because it's important during any collision, right? The total momentum before is equal to the total momentum after, right? That is, any momentum lost by one object is just gained by the other. And this is actually, in many cases, even more important. We've seen that we have energy losses in a lot of cases. And so you can't just say the kinetic energy before is equal to the kinetic energy after, but momentum before is equal to momentum after. So this can be much more helpful in solving problems. So I already kind of wrote some of this in. For here, we want to explain how a jet engine uses conservation of momentum to create thrust. Certainly, there's an energy analysis that you could do on this that would shed a lot of light on what's happening and help you understand it. But momentum is important too. And if you just look at what's happening, there's really some key parts that are highlighted here, right? A fan and a compressor as air comes in, which interestingly enough slows down the air, right? And then compresses it. And then it's combusted here, right? We've got this combustor or combustion chamber, and then the air goes out the back, goes through the turbine where it's accelerated, and then accelerated further with the nozzle, right? And the whole idea here, though, right, is that air exits with V2 greater than V1. That's the gist of it, right? So I wrote out just kind of the key points here. Air enters the engine at speed V1 from the fan, so if you look in the front here, and then air exits the back side with speed V2 greater than V1, right? And so that means for the air, and it really is just delta V, right? It really is just how much greater V2 is than V1. So you can imagine like a jet engine like this attached to a jet traveling through the air at, let's say, 300 and some meters per second, or about almost 1,000 kilometers an hour, quite fast. That means you could look at it from the perspective of the jet, right? That means the air is coming in at that speed, and you're having to actually accelerate it and get it to go out the back end even faster. And it's really just that delta V, that momentum that you're adding to the air, that's going to give you momentum, right? That's the whole idea, is that whatever that extra momentum is that you give the air, that's the momentum of the jet. Now, there are a few challenges here. So I wrote that equation there because that's sort of the important part, right? The change in momentum of the air equals the change in momentum of the plane. But the big challenges are air must be slowed down first. And of course, as maybe obvious, right, the mass of the plane is a lot greater. Well, I mean, you could add up enough air, it probably would equal the mass, but like some of these jumbo jets, I mean, you're looking at takeoff weights that are 500,000 kilograms, right? They're just ridiculous. But yeah, that's the other real challenge here, is that you've actually got to slow down the air, and that's what all this stuff in the front is, right? And that's because in this combustion chamber, you can't really just squirt fuel into it and light it and you're going to get the combustion that you want. If you think about, so imagine you've got like a pail of jet fuel, right? You got a room here, and you put a little pail of jet fuel in here. And then you walk into this room, which has a door, and you light a match, maybe even throw it right at it. What happens? I mean, it's not good, but it's not terrible. It's gonna, you're certainly gonna light it on fire, and like I said, it's not a good thing, but it's not terrible. Now, leave this bucket of jet fuel sitting in this room for like an hour, just sitting there, and then come back and light a match. What happens? Right. Well, you're gonna put a hole in the earth now, because right during that time, what has a chance to happen is that fuel has a chance to become vapor and mix with all the air, more importantly the oxygen in the air. So now when you light it, it can actually combust, right? Which is the real challenge with something like this. You've got air coming in at such a high speed, you need it to actually mix with the air. So interestingly, I said you've actually got to slow it down quite a bit, and just to get and compress it with this fuel, get it to actually mix, if you will. It's a real challenge. And then you've still got to accelerate it out the back faster, like appreciably faster than what it comes in at. So it's a impressive thing. It's any wonder that in piloting something like this or whatnot, I mean, you're going to use like maybe 100 times the amount of gasoline you would use, or more, in going an equal distance you would in a car, right? It's a very expensive from that perspective. One example, and I've already written it in to speed things along. We got Bruce Willis drills a hole in an asteroid approaching Earth. Hopefully everybody here is not too young to know the joke there. The asteroid splits in two, saving Earth. One piece has a mass of 3.5 times 10 to the 10 kilograms and goes off with a speed of 125 meters per second. The other piece has a mass of 4.7 times 10 to the 10 kilograms and goes in the opposite direction. We want to determine its speed. This is absolutely where you need a momentum analysis. So if we look at the situation before, I just sort of drew what might be like an asteroid, roughly round, why not? And just called it part A and part B. We know this, and just from its perspective, like, yes, it might actually be headed this way toward Earth or whatever, but we don't really need to consider that. We'll just consider the Y direction as I've kind of drawn it, right? We don't need to look at that. So we've got this asteroid basically just sitting there from its perspective, and maybe the Earth is headed towards it as far as it's concerned, right? So that means before V, so I used I here, so V initial of part A is equal to V initial of part B, which is just 0. And without speed, that means you don't have any momentum, right? So the momentum of A is equal to the momentum of B, which is 0. Now this has to be preserved. So that means the total momentum of this system after this lovely explosion is 0. So after, I kind of drew it this way and just sort of put the features on the individual parts. We've got mass A, where I've written it in as 3.5 times 10 to the 10 and shown its final velocity, and mass B, and you can see at the bottom here, its final velocity is what we want to know. Right? And so then we can write this. Now this is the real key to our analysis here, is that the final momentum in total equals the initial momentum, right? They're one and the same. They have to have the same value. So that means P final of A plus P final of B equals 0, because that's what it was before. And then I just wrote in the actual variables for momentum before. That is mass of A times V final of A plus the mass of B times V final of B must equal 0. And this is the thing we want, right? We want V final of part B. So we need to rearrange this equation for that. You can substitute the numbers in here, but I often find it more helpful and maybe just more richer as a learning experience to move the variables themselves and then substitute them in later. So that means I need to subtract this from both sides, which brings it over here and makes it negative. And then from there, we can divide both sides by the mass of B. And that's how we end up with an equation for V final of B. Then I just substitute in the numbers that we already know. Note that it is going to be a negative, and I come out with negative 93.1 meters per second. And I can kind of go back and look, does this answer make sense? Well, definitely the negative makes sense, because I'm saying that V final of part A is in the positive direction. So it makes sense that this would be in the negative direction over here. But also mass A is less than mass B, right? So it would make sense that the more massive one would have less velocity, right? To sort of balance these two things out. So yeah, that hopefully makes sense.